This video will present the PRIDE tool, which is an environment to develop critical distributed real-time embedded systems. These types of systems are found, for example, in cars, planes, and industrial robots. Their main characteristics are their inherent complexity, their safety critical and real-time demands, and that the system resources, such as memory, are limited. Our overall approach aims to provide an efficient development using a component-based approach based on our new component model called PROCOM. The system properties can be estimated thanks to different early analysis, and the generated code is optimized in order to reduce resource consumption. Let me introduce one example called Follow Me system. Its objective is to allow rental car to be brought back to the rent station by following another car. This automatic car implements 4 different modes: detecting of the car to follow, following the car in front, avoiding obstacles, and disable mode.
Next, we will demonstrate PRIDE using the Follow Me system as an example. We show the design from a top-down perspective. However, PRIDE also supports a bottom-up approach. Here the Follow Me project has already been created and populated with several components. This is the top-level view of the system. Let's create a new component for the warning functionality. We then add a port to the new component, add it to the design, and connect it to the existing components. We can dive into the hierarchy by double-clicking on one of the components. Let's check the internals of the automatic follow component. The component for detecting an obstacle in front of the car is missing from the design. Since the missing component has standard functionality, we will reuse it. To do so, we need to import it to the project from the repository. After importing the component, we add it to the design and connect it to the existing components. We can check the internals of the imported component by double-clicking it. Now the design is complete.
We would like to ensure some system properties, such as that the system will be able to detect an obstacle in time. For this, we need worst-case execution time values for individual components. You can see that multiple values have been attached to this component corresponding to the execution time values on the different platforms. When performing worst-case execution time analysis on the front obstacle detection component, we see that the detection takes no more than 40 milliseconds. Attributes can range from simple values to complex models, such as RMS, which is a language to model dynamic resource consumption. PRIDE allows different analysis techniques to ensure consistency, timing, resource consumption, and fault-tolerant properties, and also to simulate the system behavior.
Once analyzed, the system can be produced automatically, both for debug and release purposes. We suppose that the implementation of basic function blocks is provided as C source code. The developer must fill missing code parts using those basic function blocks. The build process is incremental, passing through the production of binary libraries for each composition level. PRIDE allows to model allocation of components to the nodes of the physical platform. This allocation is used by the synthesis to produce the binary executable files for each node of the system. During the development process, the user can use debug facilities such as breakpoints to observe the behavior of his application.
Let's see the result when the Follow Me system is deployed on LEGO Mindstorm. First, the car waits until it recognizes that it must follow the car in front. Then it follows this car forward and backward. When it detects an obstacle, it warns the car in front with a warning sound. Thanks for watching this video.